All right, this is the lecture video for day 21. So we are talking more about probability models today, and there are a lot of models out there that can represent these probabilistic scenarios, but the two main ones that we're focusing on are going to be the geometric model and the binomial model. Now, both of these are talking about a situation called Bernoulli trials. And these things are characterized by the fact that you always have exactly two possible outcomes. Common examples of this would be things like shooting a free throw, or flipping a coin, or looking at a particular computer chip and seeing if it's defective or not. Situations where in a single instance, the outcomes are either a success or a failure. And we're typically going to do this thing multiple times. We're going to shoot multiple free throws over the course of a game. We're going to be looking at a certain number of computer chips, etc. So the difference between these two models, a geometric model and a binomial model, is the question that we're asking about this situation. So for the geometric model, the question is, how many attempts until we finally get a success? Whereas with the binomial model, we're saying up front that we're going to do a certain number of trials. We're going to do a certain number of things, like maybe I shoot a total of 8 free throws. So for a fixed number n, we're asking how many of those are going to be successes. If I shoot 8 free throws, how many free throws do I expect to make? All right, so for this geometric model, we're going to start off by asking, all right, well, what is that probability? What is the probability that our random variable, the number of attempts it takes to finally get a success, what's the probability that that is a certain value? And so we're going to write this as the probability that x equals k. This is just like before when we said the probability that big X equals little x. It's just asking the probability that our count, our random number, this random thing, is a particular value. Okay, so let's start off with an example of this. So again, we're working with the geometric model. We're asking the probability that the number of attempts it takes to finally get a success is a certain value. So with some numbers in here, let's say that a probability of success is 0.4. And the question that we're asking is, what is the probability that it takes exactly 3 attempts in order to get a success? So let's say that this is shooting a free throw. Let's say my free throw shooting percentage is 40%. So the scenario that I'm talking about is the scenario where I go to the line and I miss, and then I shoot again and I miss, and then I shoot again and I make that. So we're asking, what's the probability of exactly this thing occurring? The probability that it takes exactly 3 attempts, in order for that to happen, I like to think of there being 3 instances. In order for that to happen, the first free throw I have to miss, which has a probability of 0.6. The second one, I have to miss that as well. And then the third one, I have to make that. And one of our assumptions for these Bernoulli trials is that each of these events are independent of each other. So if we want the probability that all 3 of these things happen, we can just multiply through. And then I believe that we get 0.144. So there's a 14% chance that it will be my 3rd attempt that I finally make my first free throw. Let's break down where these pieces came from and do this in a more general way. This first piece, this 0.6, came from the fact that there was a 60% chance that I missed the first shot. The probability of a failure is 1 minus p, in this case 1 minus 0.4 is 0.6. So put another way, remember, we say that q is 1 minus p is the probability that you miss. So we had a q probability of missing the first shot, a q probability of missing the second shot, and then a p probability of making the third shot. All right. So the probability that x equals 3, where x is the number of attempts it takes to make for our first attempt, more generally in this case is q squared times p. All right, so if we wanted to extrapolate this out, if we wanted to make this more generic rather than specifically 3, well, the probability that it takes k attempts to finally get a success Well, that scenario is where we have k minus 1 misses. So we miss all of the attempts up until certain points, and then we finally get a success. So this formula, or this equation, can be used to generate a probability distribution. So if we cycle through all the different k's, so k equals 1, 2, 3, and 4, we can see the various probabilities of getting these particular values. All right, so we can use a histogram to represent this probability distribution. Again, what we are measuring is the probability that the first success occurs at the first attempt, second attempt, etc. So just to do a quick sanity check, this bar is talking about the probability that the first success occurs on the first attempt. Well, that's going to be just the probability of a success, which in this case is 0.4, and that checks out. The number that we calculated earlier was the probability that the first success occurs on the third attempt. That's when you miss and then make. Well, that's going to be 0.144, which again looks about right. So it's worth pointing out that this thing goes on forever, right? There's certainly a possibility that it takes 1 million or 1 billion attempts to finally get that first success. There's some chance that the first success happens way out here. But for the most part, this is typically going to decay fairly rapidly, and we're usually only interested in the middle part. Okay, so now that we have a distribution, we can ask questions like, all right, well, what's the average? What's the expected value? And what's the standard deviation? As in, what's the center? What's the spread? So the expected value is going to end up just being 1 over p. We actually just have a formula for this. So in a sense, what we could do is add up each of these pieces weighted by their probabilities. And if you do a whole bunch of algebra and use a geometric series, which you may remember from calculus, this all sort of simplifies down to 1 over p. If you're curious in how that works, the book does a good job going through it. We're just going to take that as a given. So for our example here, the expected value, or the middle, the mean of this distribution, happens at 1 over 0.4, or about 2.5. In other words, we could say that, hey, the mean is right about there. Similarly, for standard deviation, we're going to just punt to a formula. We're going to say that the standard deviation is the square root of p over q squared. Again, there's a whole derivation that we could do, but we're not going to really focus too much on where exactly this one comes from. In our example, this standard deviation, this sigma, ends up being about 1.05, so the standard deviation gives us a sense of how spread out our distribution is. All right, so that's the geometric model. The other model that we want to talk about also works with these Bernoulli trials, these success or failure situations, but we're asking a different question about what we're counting. Rather than saying how many attempts does it take to finally get a success, we are instead saying, all right, if we're attempting n times, how many successes do we expect to get? All right, so here's an example. If my free throw shooting is 40% and I shoot 5 shots, what is the probability that I make exactly 3 of them? So one way that we might think about this is, well, if I were to make 3 of them, that means I'm also missing 2 of them. So what we're talking about is making a shot, making a shot, making a shot, and then missing 2. And then if we multiply all these things together, that gives us a probability. The problem is that probability is the probability that I do this in this particular order. The probability that I make the first 3 and then miss the second 2. I also have to consider the probability that I miss the first 2 and make the next 3. Or maybe I miss the first one, make 2, and then miss the next 2, or some combination of these things. One way of thinking about this is to use a tree diagram. So I could have my tree diagram where I make the shot versus miss the shot, and then again I make it or miss it, and then make or miss, and then one last make or miss. Let's say that the upward branch is making it, so there's a 0.4 chance of making the first shots, 0.4, 0.4, so these are the going upwards is a success, and then downwards is a failure. So one of the ways in which I make exactly 3 of the 5 shots is to succeed, 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 fail, fail. So this node here corresponds to one of those scenarios. I could have also done this in a different order. Let's say that I succeeded and then failed, so a 0.6 here, and then succeeded and then failed and then succeeded. So I'm only drawing part of this tree, but hopefully you can get the picture. So 0.6, 0.4, 0.6, 0.4. All right. So this node here is another situation in which I've made exactly 3 of the shots. And the probability of that occurring would be 0.4 times 0.6, 0.4, 0.6, 0.4. And the point I'm trying to make is the probability of being here is the same thing as the probability of being here, which we found with this one. So if I want to know the total probability of making 3 of the 5 shots, I need to add together all of these different nodes. Well, since they're all the same, I just have to multiply by how many there are. All right, and that's actually sort of almost a tricky thing to count. All right, so thankfully we have a formula to do this counting for us. And we're not going to delve too far into how exactly this thing works, but just the broad strokes are that combinations is a way of counting how many ways there are to rearrange something. So for example, if we are counting the number of ways of rearranging picking k successes out of n attempts, well, that's just going to be this combinations formula thing. So there are a bunch of different ways of writing this. Probably the most common is this first one, but you also see the second one fairly often. Depending on which type of computer software you're using, something like Wolfram Alpha likes this format, and RStudio likes this one. But regardless of how it works, what all of these things are doing is finding n factorial over k factorial times n minus k factorial. And if you haven't seen factorials before, don't worry about it. Again, we're not really diving into what this is doing. But the point is that we are adding up all the different ways of ordering something. So for example, in the shooting 5 shots example that I was just talking about, if we're talking about the different ways in which I could make 3 of them, well, I could have a success, 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 failure, failure, or maybe some other order, etc. And there are, a lot of these. And one thing we could do is list them all out. But the other thing we could do is realize that, well, n is 5 and k equals 3. So the number of entries in this list is just going to be the combination of 5 and 3. So if I were to plug combinations 5, 3 into R, I should get out 10, I believe. There are a total of 10 things in this list. So if I were to scroll back up to this original question of what is the probability that I make exactly 3 of 5 shots? Well, I've said that the probability of being here is this term, which, by the way, is about 2%. So there's a 2% chance of being here, there's a 2% chance of being here, and there's a whole bunch more of these possible ways of getting this 3 of 5 possibilities. We've said that there are 10 things in that list, so the total probability here is going to be 10 times the probability of one of these things. Remember, we said that these are all going to be the same probability. So in this case, the answer is going to be 10, because there are 10 combinations of these orderings, times this probability, or about 23%. All right, so let's fill in more of our table here. this thing that we've been talking about is the probability that this random variable ends up being k. Well, this is going to be the combination, as we just said, of n choose k times p to the power of k. So the probability of a success times the number of successes we need, the probability of a failure times the number of failures we need. Going back to our example, our answer is 10 times the probability of a success to the power of 3, at p to the power of k, times the probability of a failure, q, to the power of n minus k. So in this case, 0.6 to the power of 2. Okay, so like with the geometric model, we can use this equation to come up with a probability distribution. So make some histogram of these relative probabilities. Well, like with this, we can ask what the expected value is and what the standard deviation is. We talked about this on Monday, but the expected value should just be n times p. There's a probability p of a success. If we are attempting this a total of n times, we're adding together n copies of p. In other words, np. And then lastly, the standard deviation is going to be the square root of n times p times q. And this is one thing that I'm going to have you discuss in your groups as to why exactly that is. All right, let's take a look at one of these binomial distributions. So, like with the geometric distribution, we have that formula that can tell us what the probability that our random variable is a certain value, and we can apply that to each of the, in this case, 5 possible outcomes. I can make between 0 or 5 of my 5 attempts. And we can see what the distribution looks like. So in this case, the expected value, or the average number of shots made, is going to be 5 times 0.4, or around 2. And the standard deviation is going to be just a little bit over 1. Okay, so that's great and all. And if I was asking, all right, what's the probability that I make exactly 3 free throws? Then this formula is great. It just tells me what that number is. I might also ask, what's the probability that I make 4 or more free throws? Well, that's going to be the probability of making 5 free throws plus the probability of making 4 free throws. So I can add these numbers together. So this formula is still great. All right, what happens if instead I let the number of trials get really big? What if instead of 5 free throws, I'm shooting something like 100 free throws? All right, so here's the probability distribution for the number of free throws made out of a total of 100 attempts. And we can see that we have these bars, or in this case lines, and if we wanted to know the probability of making exactly 45 of the 100 shots, that's going to be the height of this bar. Okay, so the problem with this formula, with applying this formula for some more generic questions, is that if I asked, all right, what's the probability that I make more than half of my shots, so more than 50%, well, I could use this to find the probability of making 51 plus the probability of making 52, etc., but I have to go all the way up to 100. So that would be the exact answer, but we can use our knowledge of the shape of this picture to do this another way. So hopefully this curve reminds you of something. And as it turns out, the binomial model can be approximated by a normal model. So this is kind of surprising maybe that we have this discrete situation, right? With the binomial distribution, the outcomes have to be, these integers. We can't possibly make 2.7 shots. We're making either 2 or 3 shots. But this discrete distribution, when you start to deal with large sample sizes, so the larger n gets, the more this looks like a normal model. And hopefully this picture looks pretty similar. I think I can even turn on an actual normal model, and we can see how closely this follows. Okay, so if we have questions asking about the range of possible outcomes in a binomial model, we can use the normal model to answer those. For example, if I was asking, what's the probability that I make more than 50 shots, rather than adding up a bunch of iterations of this equation, we can use this normal model to find that range. We can find the mean and the standard deviation, which tells us the exact shape of this normal model. Now, for a small sample size, so let's go back to our first example where our n equals 5, I can turn on the normal model, and we can see that, yeah, it does a reasonable job, but it's not quite right in a lot of places. We have sort of these gaps in this picture, sort of illustrating that, hey, maybe this is a little bit inaccurate. So these gaps occur in any of them, but for a small sample size, the normal model becomes a worse approximation for the binomial model. That said, it's usually pretty good. One way to simulate this is with this thing called a Galton board. So the idea is that we have a board with a whole bunch of metal pins in it, and we're going to drop beads through the top, and as they roll down or as they fall down, they're going to hit the various pins and bounce around. We can think of each pin as a choice that the bead has to make whenever it gets to it. It has to either go left or right, and by making a sequence of choices, a bead might find its way down into one of the slots in the bottom. Right. So it's certainly possible that a bead would sort of choose to go left each time and end up in the far left slot, but it seems more likely that it would, somewhat alternate and end up relatively near the middle. So we can use this to simulate a probability distribution. So if we're actually trying this with, 100 beads, we can visually see where how many end up in each of the different slots. Because there's randomness involved, this shouldn't exactly match the answers we were getting for the theoretical probability distribution for a binomial model. But, we would imagine it would be relatively close. And then we can actually see this in action, where we turn it to start the beads, and we see that the ending distribution looks pretty similar to what we've been talking about. There's one last distribution that we're not really going to talk about in this class, but that I wanted to point out that it exists, and that's the Poisson distribution. So rather than working with Bernoulli trials, where we've got a certain number of instances and we're asking, is this a success or failure, the Poisson distribution just works with how many instances we have. So this was famously started to use when trying to count some number of cases. So I believe it started with leukemia cases. And a country or a city could ask, all right, how many cases do we expect to get in a certain year? And just by paying attention to this one parameter, we typically get 6 cases per year, we can ask, all right, well, if that's true, then just due to this randomness, how many cases do we expect to get in the next year? Well, this is also going to follow a probability distribution, and we have formulas that let us do this. Namely, we have this exponential. Let's not get bogged down in the details of that, but the point is just that the difference that a Poisson distribution makes is that rather than working with a success or failure, we're just working with counts. This only works if the number of instances is much, much lower than the population. So we're talking about a handful of leukemia cases out of a population of 1 million.